Hi there, everyone. It's Mrs. Dunn. What we're going to be doing in this screencast is we're going to be solving applied problems involving exponential growth, and we're going to solve applied problems using compound interest. This section is very calculator heavy, so I wanted my calculator here in our screencast so I could help you with some features on your calculator that will help you complete it more easily. So let's get started. What we're going to start with is this population growth model. This is an equation that you can use to model exponential growth. Let me explain the terms or the variables in this model. In this model, P is the population after time T. So T is the time, P is the population. P sub 0 is the population at time 0. It's like your initial population. And K is the population growth rate. You can use this model to describe any kind of population growth, whether you're talking about the growth of actual population, people growing in a city, or if you're talking about the growth of bacteria, or the growth in the use of cell phones, or if you're talking about the growth of money. All of these examples follow this basic graph, which we've been studying this chapter, which shows exponential growth. This is the equation for that model graphed. Okay, so let's look at a specific example. So in our first example, Raleigh, North Carolina is one of the fastest growing cities in the U.S. In 2014, the population was approximately 438,000 people, and the growth was about 3.4% per year. So what we want to do is answer these questions. We want to find the exponential growth function. We want to estimate the population in Raleigh in 2019. And we want to know when will the population be 1,000,000. And we want to find the doubling time. We're going to go through this one question at a time. So first of all, to find the exponential growth function. The initial growth, see, we're going to be filling in this equation. The initial population is 438,000. The other variable we know is that the growth rate is 3.4% per year. That's going to be our K value. So the population model, so when you plug those values into the formula, you have the population at time t is going to be equal to 438,000 times e to the 0.034 t power. And that is the exponential growth function model. So the next question we have to answer is we want to know when is the population in Raleigh going to be what is the population going to be in Raleigh in the year 2019? Well, if this initial population was in the year 2014, we need to subtract those 2 years to figure out what the time is. So the time is going to be 5, because 2019 minus 2014, that's a span of 5 years. And so now we're going to take that 5 years and plug that into our population function. So when we plug 5 into this function, we get that the population in 5 years is going to be 519,163 people. 163.5 people, so approximately 519,164 people. I just want to show you real quick how I did that on my calculator. So on my calculator, I just typed the 438,000, and I'm going to multiply that by e to the 0.034 times 5 power. And that's how I got that answer. So the estimated population in Raleigh in the year 2019 is 519,164. Okay, the next question that we want to answer is when will the population be a million? Well, then you are setting this equation equal to a million because remember P of t is how many people there are. So we need to solve this equation. The first thing we're going to do is divide 438,000 into a million. Now I wrote what this is as a fraction simply because I don't want you to ever clear your calculator when you're doing this. So for example, if I type in a million divided by 438,000, missed a zero there. I retyped it because I had missed a zero. So if I type that in my calculator, I get this value. And you don't have to change that to a fraction. I'm just encouraging you not to clear your calculator. Leave that there. Because in the next step, let me finish with this formula. We want to find t. So since we have e to this power, I hope you remember from previous screencasts, we're going to take the natural log of both sides because that's going to make our life easier. So the answer, so when we take the natural log of both sides, on the right side, that expression reduces to 0.034t. So if we want to solve for t, we're going to divide the natural log of 500 divided by 219 by 0.034. Now remember, this 500 divided by 219 is this number, right? It's this number 2.28. So I want to take the natural log of that number. So I'll type natural log and I use the second answer feature. So what that does is tells your calculator, use this answer. And then I'm going to divide that by 0.034. So basically I typed this into my calculator. And so the answer is the time is going to be approximately 24.3 years. And so the population will be a million in 24 years. So, or in the year 2038. Okay, the next thing we're asked is to find the doubling time. Well, think about this. If we're finding the doubling time, that means if the population is 1, we want to know how long it's going to take for the population to be 2. So this is going to be the same answer if I had put 438,000 and twice that on the other side. So basically, if there was 1 person, how long is it going to take for there to be 2 people to double the population at this rate? So once again, we're going to, well, we could divide by 2, and then we're going to take the natural log of both sides, or sorry, divide by 1. So then we're going to take the natural log of both sides. So we have the natural log of 2 is equal to the natural log of e to the 0.034t power. We do that to simplify the right side to 0.034t. And then to solve for t, we'll divide both sides by 0.034. And when we do that, we get 20.3839. So it's going to take approximately 20.4 years for the population to double. All right. Now let's switch our attention to money. So, before I get there, sorry, I forgot to mention. So here are some simplified expressions to find the doubling time, okay? And you're going to use this expression whenever you're trying to look for the rate. That's what K would be. And if you're looking for the time, you can use this expression. Remember, that's what we just did. We took the natural log of 2 and divided it by the growth rate in the last screencast. Okay, so in this next example, we're turning our focus to money. And this is an example about interest compounded continuously. So suppose that $15,000 is invested at an interest rate of 5.8% per year, compounded continuously. You want to find the exponential function that describes the amount in t years. You want to find the balance after 1 year, 5 years, and 10 years. And you want to find the doubling time. One thing at a time, let's talk about this exponential function to describe this growth. So what is PO? P sub 0. That's the initial amount. In this problem, that is 15,000. And the interest rate is 5.8% or 0.058. So we're just going to take those values and plug them into the equation. And so the exponential function is 15,000 times e to the 0.058 t power. Okay, next we want to find the balance after 1 year, 5 years, and 10 years. Let me clear my calculator because I want to show you this is a kind of cool feature on your calculator. So the first thing we want to do is we want to find the amount that's in the balance after 1 year. So we can type that in our calculator. So we'll type 15,000 and times e to the 0.058 power. And so that's how I got the answer of $15,895.72. I'm always going to round it to the nearest penny since we're talking about money. Okay, now you have to find out how much is in the account after 5 years. Okay, so you have to plug 5 into this equation. So just to save you some time, you can press the second enter button on your calculator and it pulls up what you just typed, and press the back arrow, and then I'm going to say multiply that answer by 5. And that's how I got the answer of $20,046.41. And then to find the amount that's in the account after 10 years, press second enter again, and then I can go back and change that 5 to 10 and press enter, and the answer is, oh, sorry, it went too fast, $26,790.58. That's kind of a cool feature on your calculator. I've used that several times, especially in your homework. You're going to notice you're going to get like a bunch of questions in a row where all you have to do is change one number, and that'll help you. Okay, the last question is to find the doubling time. Remember, if we're finding the doubling time, I'm going to pause the screencast and go back to the one I want. So remember, we want to find the time it's going to take for the money to double. So which one of these formulas should we be using? Hopefully you recognize that we want this formula for where we're looking for the time. So we're looking for the time, and like I just said, we're going to be using the t is equal to the natural log of 2 over k. K, remember, is the interest rate. So it's really simple in this problem because the interest rate is 0.058. So we simply just type that in our calculator, the natural log of 2 divided by 0.058, and press enter. And it looks like it will double in approximately 12 years. So I put 12.0 to show that rounding. See how it says 11.95? So if I'm rounding to the nearest tenth, I have to round that up. I show the rounding by adding the 0. And that's it. Good luck. I hope these examples help you with this section.